In the last session, we talked about stoichiometry and how it's needed to convert from grams of one thing or find the quantity of one substance from another. Stoichiometry is a matter of taking one substance and one quantity and finding another quantity. Unfortunately for us, a lot of times in chemistry, we're given more than one quantity of reactant. You're given the quantity of several reactants, and then from that, you have to figure out a quantity of some product. So instead of just having one number given to you and finding one other number, you are given multiple numbers, 2, 3, 4, or an infinite number of numbers, depending on how many reactants there are, and it has to find something else. So it becomes a little more complex than just shooting straight forward. In this case, we have to determine which one of these substances that you're given is going to affect our product the most, or be what we call the limiting reactant. The limiting reactant is defined as the substance that completely is consumed by the reaction, thereby ending the reaction. Let me give an example you can relate to. Hopefully you've made s'mores at some point in your lifetime. And for this example, making s'mores is going to help us explain what a limiting reactant is. Let's say we're going to make s'mores and we go to our kitchen cabinet and we find in our box that we have 30 graham crackers. All right, so that's 30 graham crackers, and so if we snap those in half, we have enough to make 30 s'mores out of them. All right, we then go find a bag of marshmallows, and we find that we have in the marshmallow bag 22 marshmallows. We continue on and find our chocolate, and in the cabinets, the only thing we can find are Hershey bars, and we have enough pieces of chocolate to make 18 s'mores, so 18 pieces of chocolate. Now, if we were making s'mores, these would be our reactants. We're putting these things together to make our product, which is one s'more. Now, we know that each s'more takes 1 graham cracker, 1 marshmallow, and 1 piece of chocolate. Okay, so our ratio is 1 to 1 to 1. We need a whole graham cracker to break in half. We need 1 marshmallow. We need 1 piece of chocolate. So given that reaction, the thing that we would limit our production and cut off our production would be the chocolate, because once we made 18 s'mores, we would no longer have chocolate remaining. Since the chocolate would no longer be remaining, then that means we can't make any more. We have enough of the graham crackers to continue on, and we have enough marshmallows to continue on, but to completely make s'mores, we can't. Therefore, the chocolate would be considered our limiting reactant. Since we have more than enough of these two things, they are considered to be our excess reactants. Excess reactants are the things that you have more than enough of, and at the end of the reaction, you have excess. You have some still remaining in the reaction vessel. So if I made those, I would have 4 marshmallows left over, and I would have 12 graham crackers completely left over. All right, so those are the excess reactants. So that gives you an analogy of what limiting reactant is. Now let's look at how that relates to real chemistry. In this problem, the first example we are reacting 637.2 grams of ammonia with 1,142 grams of carbon dioxide in the reaction given. We want to do 2 things. We want to determine out, actually we want to do 3 things. We want to figure out which of those 2 things is a limiting reactant, meaning which one's going to run out first. We also want to figure out how many grams of the NH2CO is going to form. And then we want to figure out whichever thing is the excess, how much of that would be left over. Parts A and B you're basically going to do in the same step. And what we do in this case is we're going to just make an assumption like we would have done before. In the last section, if I had given you just that number and said find the grams of NH2CO, you would have done a straightforward stoichiometry problem. However, in this problem, we don't have just one number. We have both numbers. So what you do in this case is if you're given more than one quantity and asked to find another quantity, you have to take first each of those problems and treat them as a separate problem. So we're going to take our ammonia and we're going to take our carbon dioxide and treat them as 2 separate problems, and we're going to find the answer to this in both cases. So before we do anything, we know the first thing that has to be done is we have to balance this equation. So we start off with nitrogen. I have 1 nitrogen on this side, 2 on this side, so put a 2 in front. I have 6 hydrogens now on the left. I have 2 times 2, which is 4 hydrogens, plus 2 more here. I have 6 hydrogens on the right. Carbon, I have 1 carbon on the left, I have 1 carbon on the right. Oxygen, I have 2 on the left, right there. And I have 1 plus 1 is 2 on the right. So we are now balanced. 2, 1, 1, 1 is our balancing numbers. Next step, what do we know? We have 637.2 grams of this. We have 1,142 grams of this. We want to know how many grams of this is going to form in the end, and we want to know which of these two things is our limiting reactant. All right, so here we go. We start off with each problem. 637.2 grams of NH3 times 1 over the molar mass, which is 17 grams. So we're going from grams given to moles given. All right, so if I stopped right now, I would have moles of NH3. It's not what I'm looking for, so I'm going to continue on in my diagram. Next thing I'm going to do is go to moles given to moles wanted. Here's the substance I want. Here's the substance I'm given in this case, so the ratio is 1 over 2. So there's 1 NH2 2CO per 1 NH3, sorry, per 2 NH3, sorry. All right, so again, that gets rid of moles of NH3, so now I'm left with moles of NH2 2CO. I want grams of that, so I need to continue on. I need the molecular mass, so off to the side I have 2 times 14, which is 28 grams of nitrogen, plus 4 for the hydrogens, plus 12 more for the carbon, plus 16 more for the oxygen, giving me a grand total of 60 grams. So there are 60 grams per 1 mole of that substance. Okay, so we could mathematically then solve that and find our answer. And while you may be doing that, I'm going to go ahead and set the next problem. 1,142 grams of CO2. I'm going to convert to moles, so 1 over 44. So that gets rid of grams of CO2 and have moles of CO2. Now to go from moles of CO2 to moles of the product, I have 1 mole of NH2 2CO over 1 mole of CO2. Again, we're getting those numbers right here in front. There's 1 in front of both of them. And then again, the molar mass of that is 60 grams per mole. Now that I have both problems set up, I can punch them into my calculator and solve. So, in the first calculator, I have 637.2 times 60 divided by 17 divided by 2 gives me 1,127 or 1,128, we'll say, grams of NH2 2CO. All right, so if NH3 is our limiting reactant, that's how much it would produce. Now, let's try the other problem. We start with 1,100. Let's start over again. 1,142 divided by 44 times 60. And again, it doesn't matter which order you did it. If you did 60 divided by 44, it's the same thing. Gives us an answer of 1,557 grams of that substance. Since we've solved both problems now, this is the lowest answer. Therefore, we call this our theoretical yield. What a theoretical yield is saying is, in a perfect world, if I did that reaction with these quantities, this is theoretically how much I should be able to produce. Since the ammonia gave me that answer, that means that is the lowest answer of the two, and that's why we chose that one as our answer, because it's the lowest answer of the two. You always choose the lowest answer. Since ammonia gave me that answer, we say that ammonia is our limiting reactant. All right, so if I had to solve for something else now, if I had to solve for water as well, I could just simply start with my ammonia because I know that's my limiting reactant. Once the limiting reactant is established, that is what you will use as your starting point from there forward to solve anything else about that problem. CO2 is our excess reactant. We have more than enough CO2 to begin with. Now the question also asks us, So the answer to part A is what is the limiting reactant. Well, the answer to the limiting reactant is there. That's part A. The answer to part B is how many grams is formed. That's the lowest answer, which is there. Now the answer to part C we get by simply doing another stoichiometry problem, and this time it's pretty straightforward. Since I know my limiting reactant is NH3, I'm going to start with that, 637.2 grams of NH3. And I'm going to find how many grams of CO2 are used. When you start with one reactant and you find the quantity of another reactant, you are finding how many grams are used or how many grams are needed. All right, so let's figure out how many grams were actually used. So again, there are 17 grams of NH3 per mole. The ratio of CO2 to NH3, what I want over what I have, is 1 to 2. So there's 1 CO2 for every 2 NH3s. And then the molar mass, or molecular mass of CO2 is 44 grams per mole. All right, so again, with my calculator, I put in my numbers. 637.2 divided by 17 divided by 2 times 44 gives me 846.6 grams used. Again, that's how many grams there are, that's how many grams were used. Now the question doesn't ask how many grams were used, the question asks how many grams are left over, how much excess reactant remains. So if that's how much is used, and we know that this is how many grams we began with, we would simply subtract those two to get how many grams are left over. So if we had 1,142 grams to begin with, and we subtracted off, or we used up 846.6 grams of that, that means we would have, oops, must have done something wrong. Let's try that again. 1,142 minus 846.6 means we would have 295.4 grams CO2 left. All right, so that is how many excess reactant remains. All right, so moving on from there, in your notes now, you have yet another problem here to do. So let's continue on and try another problem. Again, if you want to try this one on your own without my help, pause the video right now and then come back and restore the video once you've finished in your notes. In this example, it says 124 grams of aluminum are reacted with 601 grams of iron 3 oxide in the following reaction. And the reaction is not given because I want you to write the reaction. Same thing, we want to figure out what the limiting reactant is, how many grams of Al2O3 are formed, and how much excess remains. Again, A and B will be done at the same time. So the first thing we need is a balanced equation. So let's start with that. We are reacting aluminum with Fe2O3. And when I look at that, again, we identify that as a single replacement, a single element reacting with a compound. In this case, my single element is a metal, therefore it will replace the metal of the compound. So aluminum is going to join with oxygen, and off to the side we say aluminum is going to be plus 3. Oxygen is going to be minus 2, so it's going to form Al2O3. And then iron is going to go off by itself. But we need to balance the equation, so I've got to put a 2 in front of the aluminum. I've got to put a 2 in front of the iron. So it balances 2, 1, 1, 2. Now, we are given that we have 124 grams of aluminum, and we are given that we have 601 grams of Fe2O3. So each of those problems, since we want to find Al2O3 in our answer, we're going to solve for that. And whichever one is the lowest answer is going to be our theoretical yield, or how many grams are going to be formed. That'll be the answer to part B. So let's go from there. 27.0 grams of Al per mole of Al. Ratio of aluminum oxide here to aluminum is 1 to 2. There's 1 Al2O3, which is what I want, over 2 Als. Then off to the side, let's figure out our molecular mass. So 54 is the mass of 2 aluminums, plus 48, which is the mass of 3 oxygens, 3 times 16, gives me a total of 102 grams per mole. Down below, we have to start off with our molecular mass of our iron oxide. Iron is 55.8, so 2 times 55.8. Equals 111.6 for the iron, plus 48.0 for the oxygens. Gives me a total of 159.6 grams per mole. Again, from this point, we look at our ratio. Ratio of iron oxide to aluminum oxide is 1 to 1. So there's 1 Al2O3 over 1 Fe2O3. And then again, the aluminum oxide molar mass is 102 grams per mole. Now that we have both problems set up, we can solve this problem now and see what we get. So with our calculator again, 124 divided by 27 divided by 2 times 102 gives me a total of 234 grams of Al2O3 would be generated from the first reaction. So if we just had the aluminum given, that's how many grams would be produced. If we're using the other number, 601 divided by 159.6 times 102, that tells me 384 grams of aluminum oxide would be produced from the iron 3 oxide. So when we look at those two answers, the one we choose as the answer to part B is the lower number. That is our answer to part B. The answer to part A then is what substance gave us that answer. The substance that gave us that answer was the aluminum. Therefore, the aluminum is the limiting reactant. That means Fe2O3 would be our excess reactant. So our final thing we have to do with this problem is to figure out how much of the excess reactant remains. And if you remember, we just said 124 grams of Al is our starting point again, because once we establish our limiting reactant, we go with that. 27 grams per mole. Ratio of what we want to what we have. There are 2 moles of aluminum for every 1 mole of Fe2O3. Fe2O3 is 159.6 grams per mole. So if we use our calculator again, we take 124 divided by 27 divided by 2 times 159.6 gives us 366.5 grams used. Since we had 601 grams to begin with of Fe2O3, we simply do some subtraction. 601 minus 366.5, and we get about 234 or 235, we should say, grams left over. Okay, so that's how you find limiting reactant and excess reactant and theoretical yield and how much is left over and all that stuff. Again, theoretical yield is in a perfect world how much we produce if those two things reacted together. And all we did was take both numbers and we solved for them, and the lowest answer was what we call our theoretical yield. Now, in the real world of chemistry, what we find is our theoretical yield, what we actually should be producing, or what we think we should produce based on the numbers, and what we actually do produce when we carry out the reaction are completely different. The amount that we get when we carry out the lab is called our actual yield. So if I took this lab and I carried it out, and let's say I did the reaction, and in the end, I get 225 grams of Al2O3. All right, so that's what I actually got. And I know things are cluttered there, and I apologize for that. So if I actually get 225 grams, and I was supposed to get 234, one of the things we need to calculate generally for purification's sake and some of the other issues we look at later on is what's called a percent yield. To find a percent yield, you would simply take how much you actually did produce divided by what you should have produced times 100. So actual over theoretical times 100. And in no circumstance should you get over 100%, because we just said actual yield should always be less than theoretical, so you should always have a decimal less than 1. If you do get a number over 100%, that means you have contamination. And to a chemist, the number less over 100% is definitely grounds for bad results. On the opposite end of the spectrum, we don't always need to be near 100%. Some reactions are looking for only around 15%, some around 30%. So every reaction is different as to what you're looking for. It really depends on a lot of different factors. So in this case, to get our percent yield, we would take the number that I just gave you, and in the problems you would be given on a test or a quiz, you will be given an actual yield in a problem. In a lab setting, when we do the lab, you'll have to find the actual yield and calculate theoretical yield at the same time. We would take 225 grams divided by 234. So this is what we actually did get. This is what we're supposed to get, times 100. And we would punch that in a calculator. So we would say 225 divided by 234 times 100. And we would get 96.1 or 0.2% yield. All right, so this wraps chapter 3. Talking about limiting reactants, theoretical yields, excess reactants as a recap, because this is a very important section. A limiting reactant is the substance that runs out first in a reaction. It is the substance that is completely consumed by the reaction, and it ends the reaction. That's why it limits the product. It is the substance that will give you the lowest yield when you do the stoichiometry. The excess reactant are all other reactants that give you the higher amounts. The amount given to you, the answer given to you by that limiting reactant, that lowest answer, is called your theoretical yield. Theoretical means in a perfect world, in theory, that's how much you should be able to make. In real life, your actual yield when you carry out a lab is generally or always less than that. If it's not, that means you did something wrong in the lab setting. Okay, so this wraps chapter 3. You have some problems to do for practice.